So yeah, hello everyone. A very good evening. So let's wait few more minutes so that everyone can able to join the session. Okay, so let's start this session. So hello everyone, a very good evening, and just let first confirm me whether I'm audible and visible. Okay, okay. So my name is Pooja Verma, MPMRF Research Scholar from IIT Kharagpur, and course instructor for this course is Dr. M.K. Bhuvan, Department of Electronics and Electrical Engineering, IIT Guwahati. This is a week 9 live and interactive session on computer vision and image processing, fundamentals and application. So I hope all of you have gone this week video lectures this time as well. So here we will solve some problems which will be similar to your assignment question. I hope. So let's see. So this is a week 9. So we will solve some again some numericals and problems based on image descriptors and features. So yeah, this is our first question. So question is what is key advantage of Harris corner detection over earlier methods like the Moravec corner detector? Option A, it uses color information instead of grayscale. Option B, it is a rotation variant. Or option C, it avoids explicit eigenvalue decomposition. Or option D, it detects edges instead of corners. Which option is the correct one? Would you like to answer for this question? Please try to answer, then we will discuss in detail. Okay, Anand is giving answer C. Okay, anyone else? Okay, okay, so let's see the detailed explanation here. So yeah, so we will go through the options and we will check which one is the correct option. So first we will see what is a Harris corner detector and Moravec detector. So the Harris corner detector was specifically designed to address the limitation of the earlier Moravec detector. So key advantage or primary weakness, one of the primary weakness of the Moravec was its lack of isotropy. It's only shifted window in 4 or 8 discrete directions. That is a 0, 45 degree, 90, and some other angles itself. So our option A is it uses color information instead of grayscale. So if we have gone through that, so both the traditional Moravec and standard Harris algorithm that operates on the grayscale intensity values only. So while color extensions exist, it is not a defining key advantage of the original Harris methods over Moravec. Okay, so it is not a correct option. So because it's primarily working on the or operating on the grayscale intensity value, not a color information. So option B, it is a rotation variant. So in the Harris and Stephens that improved by this using the differential or corner score with respect to the all possible directions directly. So that makes the detector robust to image rotation as a corner response to the remains consistent regardless of the angle. So it is a rotation invariant, not a rotation variant. So our next option is option C. It avoids explicit eigenvalue decomposition. So in the Harris corner detector, that does avoid calculating the actual eigenvalues lambda 1 and lambda 2 by using the determinant and trace of the matrix. That by defining this equation. So that makes it much easier than the methods that require full decomposition. And the Moravec's method did not use values, and it uses simple intensity differences in few directions. So that Harris introduces a mathematical framework based on the second movement matrix. We will solve some numericals on that, and that matrix is defined by its eigenvalues. So that Harris shortcut formula that allows to get the results without solving the characteristic equation. So our next option is it detects edges instead of the corners. So the both algorithms that primarily designed for the corner or entrance point detection, and that Harris is better at distinguishing between the edges and corners, but it depends. It does not replace corner detection with edge detection. So the correct option is option C. It avoids explicit eigenvalue decomposition. That is the not a key, but this is the advantage in the all other options. Okay, so option C is the correct answer for this question. Is it fine to all of you? Can we move our next question? Okay, so moving to our next question now. The next question is the histogram contains 9 bins corresponding to angle 0, 20, 40, 60, 80, 100, 120, 140, and 160. So given gradient magnitude and direction matrices are given. Okay. So now question is compute the vector representing the histogram of the gradient corresponding to the following details. So now we need to compute a vector that represents the histogram gradient for the given angles. Here magnitude and direction matrices are given. That one is a magnitude matrix and this one is a direction matrices. So how we can calculate with this question? Anyone having any idea how to proceed with this question? We will solve in detail here step by step. Anyone would like to answer? Okay, so let's solve this question. So here the histogram that consists of 9 bins with the angles. It is given here 0, 20, and the gradient and the magnitude and the direction matrices are given also. So here the each magnitude contributes to the bin corresponding to its angle. Like uh, corres- to there is a magnitude 2 and their corresponding angle will be the 80, right? Like this. So if the angle falls exactly on the bin center, the full magnitude is added to the bin, to that bin, and if it is falls between the center, it is split proportionally between them. Okay, not like that. So like here magnitude is 2, right? In the first magnitude is like 2 and angle like this. So if magnitude here the first matrix that 2 and angle is 80, so that is falls exactly on the 80, right? So we need to add 2. Add 2 at the angles are given. So in that location, we have to add 2. That means how many numbers? At win 5, right? So at win 5, in the angle 80, we need to add 2. Okay. At the because we need a corresponding gradient magnitude, not an angle. So at this angle, we need to add 2, otherwise 0, right? Now the next, the magnitude is 3 and the angle is 100, right? So at that corresponding angle, that means at here, we need to add 3 in the gradient. Okay. Now similarly in the same way, at the magnitude is 4 here and angle is 100, right? Again 100. So now at 100, at this angle, we need to again add 4, right? Because we are just calculating the gradient of the corresponding angle. So again at 100, we need to again add 4. Now next one is magnitude is 7 and angle is 40. So at angle 40, we need to add the 7. That 7 in the corresponding magnitude. So we will see we will write here. So first one is 0, right? 0 angle it is given. Then 20, then 40, 60, 80 and 100. So at 0th angle, right? So no gradient or magnitude is given. It will be the 0 only, right? Now in the next 20, so no angle it is given in the matrix 20. So again the 0 will be there. Now next at 40, so at 40 we need to add 7. At angle 40 we need to add 7 in the gradient, right? In the magnitude. So 7. So we have to add 7 here. So it is 0, 0 plus 7, 7 will be there. Now next angle is 60, right? So let's check in the, so there is a no angle and at that angle there is no magnitude or gradient is given. So again it will be the 0 only, right? So now next angle is given is 80. So here if you check that 80 is given and corresponding magnitude is 2. So what we need to do? We have to add 2 in this gradient. Now next one is 100, right? So at 100, if you see that here two magnitudes are given. First one is add 3, then add 4. So first we need to add 3 and that angle, then again we need to add 4 also. So 3 plus 4. So total 7. So we need to add 7 at angle 100. Okay. So now again 120 it is given. So at 120 there is a no angle and corresponding magnitude is given. So again it is 0. And then again 140. Again nothing is given. So again we need to add 0. Now next one is a 160. So again no angle it is given. So we need to add 0 here. So now what is our vector representation of that given histogram gradient? So how we can represent it? Like start from here 0, 0, then 7, 0, 2, 7, 0, 0 and 0. So this is a vector representation of the gradient for the given corresponding angles, 9 bins of the corresponding angle. So if you check that option C is this one is the correct option 007, 027, 000, right? So is it fine to all of you? Any doubt? Okay. Okay, so Anand is writing something no. What does it means? Is it fine, Anand? Okay. So any doubt, any problem? You can ask, otherwise we can move to the next question. Can we move to our next question? Okay. So moving to our next question. So now next question is here image matrix, that is it is given. So I it given it is a 5 cross 5 matrix, if you see that image matrix, and here d by dx and d by dy, it is also given the gradient of the in the direction x and direction y, right? Or you can say that horizontal gradient and vertical gradient also given. Now they are asking in the question, compute the Harris matrix of 3 cross 3 highlighted window. So this is our highlighted window. If you see that in the image, right? This one, this 3 cross 3 is our highlighted window. Now we need to compute the Harris matrix for the given matrix. Okay. Now how we can compute this one, this question? Anyone, any idea? Then we will solve this question as well. Okay. Multiply d by dx row wise, then okay. Yeah, correct, Nand. We will solve it. So to compute the Harris matrix, and that Harris matrix is also known as a second moment matrix, as you know that. For the highlighted this 3 cross 3 window. So let's say this highlighted 3 cross 3 window we will represent by W. Okay, so this is our highlighted 7, 8, 9, 12, 13, and 14. This one is a 17, 18, and 19, right? And our gradient kernels are in the x direction -1, 0, 1, and in the vertical direction it is a -1, 0, 1, right? Again, so for that each pixel in the 3 cross 3 window, in this window, we will apply the kernels. Okay, yes, Swati, so first we will compute the horizontal gradient, that is called Ix. So how we calculate the horizontal gradient Ix? So I take another slide so that we can put it there. Okay. So first we will calculate the horizontal gradient Ix. So for calculating Ix for any pixel in the window, what we will need to do to calculate, that is Ix. So I here you can say that row into column plus 1 and minus row, here it is a plus, column minus 1 we need to calculate. So in the given image every horizontal neighbors differs by 1. If you see that this one, this one, if you are moving horizontally, every pixel is differs by 1. So 7 plus 1, so 1 difference, 8 plus 1, 9, that is 1 difference, and also 12, 13, 14. So there is a 1 difference by each pixel matrix, and 17, 18, 19, right? So if you, for example, if you calculate for any pixel, let's say if we are calculating for the center pixel, right? The center pixel is 13. So how we can calculate Ix for the central pixel? So row, like second row plus colon minus 1. So that means this, and colon plus 1 for the this one. So that means 14 minus 12. Okay. So for the, to calculate for the center pixel, we will take the next two column value by taking the minus. So 14 minus 12. So we will get 2 here. Similarly, if you calculate for the 8, let's say, so for the 8, you have to take column this minus this. So you will get 2 here again. And similarly, if you want to calculate for 18, again for this, so you will get 19 minus 17, like that. You will get all the values for any value you to. Like if you want to calculate for 7, so for calculating 7, so next column is x plus, you can say x plus 1 for the, and for row y. So if you like 8 minus 6, you have to take like this. So again you will get 2, right? For 7, ix 7, I can write. So 8 minus 6, 2 again. And if you want to calculate for the 12, so 13 minus 11. So again you will get 2, like that. So already we have added here. So if you see that, you will get the 2 for all the values in the 3 cross 3 matrix. You will get the horizontal gradient, you will get 2 for the all the values in the 3 cross 3 given matrix. Okay. Similarly, if you want to calculate for the vertical gradient, so for any pixel window, that 3 cross 3 pixel window, so similarly you have to calculate the ix plus y plus 1, that means row above and row below for the given pixel. One row above minus one row below, or you can say that below minus above. So if you see that in the vertical gradient, so if you find that in this way, so there is a differ, every pixel is differ by the another pixel by 5, right? So 9 plus 5 is 14, 14 plus 5 is 19. Similarly, 8 plus 30, 8 plus 5 is 13, 13 plus 5 is 18, right? 7 plus 5 is 12, and 12 plus 5 is 17. So that is differ by 5, and this horizontal is differ by 1, right? So if you calculate for the vertical gradient, like if you want to calculate for the, let's say, I by for the central pixel, so 13, so 18 minus 8. So here you will get 10, right? Again, for the next, if you want to calculate for this for 14, so you will get 19 minus 9, again 10. So if you check for all the vertical gradient, so you will get 10. So for all the values you will get 10 for the IY. IY is 10, and IX, if you calculate, you will get 2. Okay. So now we will get here Ix is equal to 2, and Iy we will get is equal to 10, right? So now to calculate the Harris matrix or second moment matrix, so the Harris matrix M is calculated by, so just let me write this, then I will explain. So summation of all the value in the window, can say that Ix square ix iy ix iy iy square. Okay, so will those values always be positive or it can be negative? So it depends on question. It can be a positive or it can be a negative also. So most of the cases it will be the positive value, not a negative. Okay, Tirupatika. Okay. So ix, iy values we know. So ix square is 4, right? 2 square, here ix into iy. So 2 into 10. So 2 into 10, here again 2 into 10 and iy square, that means 10 square, right? So if you just calculate it in the matrix, you will get 4, 20, 20 and 100, right? So now now we have to calculate this summation part. So that since the gradient is constant, right, across the entire 3 cross 3 highlighted window. So in this 3 cross 3, that means total 9 pixels are there. And the gradient Ix and Iy, that is constant across the whole window, right? Horizontal gradient as well as vertical gradient is constant for all the values, right? So the total number of pixels is 9 in the 3 cross 3 window. If you check 9, so that means this summation is 9. So that is in the total numbers in the total gradient in the, that is for each gradient it is a constant, so we will calculate 1. The total summation is 9 for the given gradient, so 20 and 100. So if you just multiply, so here you will get 36, so here 180, right, and here again 180, and here if you just multiply 900, 100 into 9, so 900. So this is our Harris matrix. Okay, so 36, 180, 180 and 900. So if you check in the options, you will get option B is the correct answer for this question. Is it fine to all of you? Any doubt? Any doubt or any problem? Or is it fine to all of you? Okay, okay, so everything is clear. So moving to our next question. Okay, so our next question is related to the question 3 itself. So from the Harris corner response, what we get from the assigned area of the image given in the question 3. So option A is either a flat region, option B is corner, edge, or option C is corner, or option D none of these. So from the given Harris matrix, now we need to calculate the Harris corner response, and from there we need to get from the that assigned area what it will calculate or what it will give. Either it will give the flat region, edge, corner, or none of these. So anyone have any idea how to calculate this one? So how to calculate Harris matrix? Anyone knows? Eigenvalues. Okay. So okay. Let's see. So the Harris response is calculated using the determinant and trace of the matrix, right? So the Harris response that is R is calculated by determinant of n minus k trace of n whole square, right? The Harris response is calculated by this formula. Is it fine? Okay. So now we need to calculate the determinant of the calculated Harris matrix and the trace as well. So our Harris matrix that we have calculated previously, that is 36, 180, 180 and 900, right? So first we need to calculate the determinant of the given Harris matrix. So how we can calculate this multiply by this, right? So 900 minus 180 into 180, right? So here what we will get? Yeah, that is correct. Determinant we will get. So here if you just multiply, you will get 32,400 here minus 32,400. So again, our determinant will be the 0 here, right? Now we need to calculate the trace of the given Harris matrix. How we can calculate the trace? What will be the value of for the trace? Can anyone of you tell? Yeah, that is the sum of the diagonal element. So diagonal elements are the 36 and 900. So 36 plus 900. So 936 is the trace of the this Harris matrix. Right. Now we need to put in the Harris response formula. So R is equal to determinant is 0 hour. It is given and minus K is equal to 936 whole square. Right. So now here if you just calculate, so that is K into 936 whole square. So here, sorry, it in minus. So minus K into 936 whole square. So here K is our sensitivity constant. So K is the sensitivity constant which varies. Typically this value is vary from 0.04 to 0.06. Okay. So here the because of the determinant is 0 and the response, then response will be very large negative number, right? So now our response is a very large negative number, right? If you calculate 936 whole square, then it will give a big number. If you multiply this range, so again you will get a there is a large negative number will be there, right? So that is a very large negative number, negative number. So in the Harris corner detector, so if R is less than 0, that means a negative number, right? So that what will be indicate? It indicate as, right? Indicate as. That is correct here. And if R is greater than 0, that means there is a positive number. So it indicate a corner. Indicate corner, right? And if R is equal to 0, then it indicates a flat or homogeneous region. Flat or homogeneous region, right? So here our R is less than, so that means it indicates a edge. So Harris response indicates that an edge, right? Because it is a large negative number. Because Harris response R is a large negative number, is large negative number. So it indicates an edge, right? It indicates that area is an edge, and an area is edge. So correct option is option B. Edge is the correct option for this question. So is it fine to all of you, or any doubt in this? What about others? Have you understand this question? How to solve this question? Okay. So can we move to our next question? Or any doubt? Anything is there? Okay. So I hope all of you have understand this question. Now moving to our next question. Okay. So our next question is the matrices given below. So these matrices that represent the output after applying Gaussian filter in the image. So with different bandwidths for a single octave in a shift detection algorithm, find the key point location and scale. Now we need to find the key point location and scale. So these matrices are given now, and these matrices are the outputs after applying Gaussian filter in the image matrix with the different bandwidth for a single octave in the shift. So for that we need to find out the key point location and scale. So how we can find the key point location and scale? Anyone? Anyone would like to answer for this question, or just tell what or how we can solve this question, or any idea? So here, to find the key point in the shift algorithm, we need to find, okay, maximum value. Yeah, so we need to find the local maximum or minima in the difference of Gaussian DOG space, right? So that means finding the value that is higher or lower than all 26 of its neighbors. So here, so there is a one matrix. Just let me go. Okay, we will solve it. Here, how 26 neighbors are there, and 8 in the lower, 9 in the layer above, and 9 in the layer below. So that is a 28, 26 neighbors. Okay, 8 in the layer below, or 8 in the layer above, and 8 9 in the layer, sorry, 9 in the layer above, 9 in the layer below, right? So for that we need to subtract each matrix from the one that follows it. So that means we need to subtract each matrix that follows that. That means subtract this matrix from this, and subtract this matrix from this matrix, subtract this matrix from this one, like that. Okay. So now we will focus on the middle layer. So this one, this is in the middle. So this middle matrix. So because the key point need a layer above and layer below to it. So layer above and layer below. So this is one is a layer below, and this one is a layer above to it to get an extremum. Okay. So now let so first we will go step by step. So first let's say the That difference matrix is represented by D1, D2, D3 like that. So first D1 is, let's say here Di. So Di is equal to Gi plus 1 minus Gi. Okay. So here Gi plus 1, that means this matrix, and Gi is the this matrix. So first we will calculate for D1. Okay. So D1 means G2 minus G1, right? So let's say this is our G1 matrix, this one is our G2, G3, G4, and this one is G5. Okay, this is a representation for the each given matrices. Okay, so now can you subtract and let me know what will be the value? So 25 minus 25, what will be the value? Here I am subtracting directly, otherwise it is difficult to write and just calculate it. So here just 25 minus 25, so 0 here. Now next 20 minus 22, so how much it is there? Minus 2, right? And 20 minus 20, so again 0 here, and 16 minus 17 is minus 1 here. Like that we need to subtract. Now move to our next row. So row 2, so 25 minus 25, again 0 here. 30 minus 28 here, 2. 19 minus 19 is 0, and 16 minus 17 is minus 1, like that. Now move to the next third row. So 19 minus 20, so minus 1. Here 17 minus 19, so minus 2 is here. 19 minus 19 is 0. 16 minus 17 is minus 1, right? Now to the next. So 13 minus 15, so again minus 2. So 13 minus 15, again minus 2. Here 14 minus 15 is minus 1. 14 minus 15 is minus 1. So this is our D1 matrix, right? Similarly, we have to calculate for D2. So D2 is G3 minus G2, right? If you just put here, so you will get D2 is G3 minus G2, right? So that means subtract each pixel point or each location from the given. So if you subtract it, what values we can get? Anyone can tell? Just make it interactive so that we can able to solve it. Can you tell the values? Can you subtract from G3 to G2 matrix? So 24 minus 25 is minus,
minus 1,
yes, and next
minus 2,
minus 2, 0, and
0, minus
minus,
2,
yeah, correct, correct. And what about the next row? The second
0,
row, 0, 2,
2,
0,
0,
and
minus 1,
yeah, correct. Next one is,
minus 1,
yeah, minus 1, then 0, then,
minus 1, 0, minus 2,
yeah, that is minus 2. In the last row, so here 12
min,
minus
mi,
30, yeah,
minus 1,
minus 1,
minus
and
1,
all are the minus 1.
minus 1, minus 1, yes, ma'am.
Yeah. So we have calculated D1 and D2. Similarly, we have to calculate D4 and D5, D3 and D4, right? Now we have to just make, take it next D3. So D3 is G4 minus G3, right? So I just remove it from here. We don't require D1 because we required layer above the center matrix and layer below the center matrix. So that means this matrix, that is D2, and D3 we required here, but we need this for the comparison purpose. So I'm just removing it from here. So I will write it somewhere. Okay, so next one is D3, right? So D3 is G4 minus G3, right? So G4 minus G3. So can anyone tell what will the values we will get here? The
minus
first,
2,
yeah, minus 2, minus
minus
3,
3,
0,
0, minus 2,
yeah, here,
minus
next,
1,
yeah, next one is,
3,
yeah,
yes, ma'am. Minus 1, minus 1,
yeah, correct. Next row,
minus 2,
0,
0,
and minus 1,
minus 1, minus 1,
yeah, correct.
minus 1, minus 1,
Minus 2 and minus 1, right?
minus 2, minus 2,
Yeah,
minus 1, yes, ma'am.
minus 1. Now, similarly, we have to calculate for D4 as well. So, I'm just taking D4. We can calculate D4 is, that is G5 minus G4, right? So, for that, I'm just calculating it here. So, what are the values we will get here? So, minus 2 and minus 5, then 0
0,
and
minus
minus
4,
4. Yeah. Next one is minus 4,
minus 4,
2,
2,
minus 8 and
minus 8,
minus 6, right?
mm,
So 0, minus 8,
minus 8,
2
2,
and minus 3. Yeah, minus 1,
minus 1,
minus 1,
minus 1,
minus.
minus 2, minus 2.
Yeah. So here this one is our D4, D3 and D2 matrix. So I can write it D1 as well. So D1 I'm just writing it here for the visualization purpose. 0, minus 2, 0 and 1. Sorry, minus 1, 0, 2, 0 and minus 1 is here. Minus 1, minus 2, 0 and minus 1. So minus 2, minus 2, minus 1, minus 1, 3 there. Right. So now we need to check the maximum value, right? Because if we are taking the minimum, so minimum is 0 and it is in many places, right? So here we will look into the maximum value. So if you see that, you will get in all the matrices in whole, you will get 3 is the maximum value. So it is located in D3, right? D3. So look at the value 3 in the center of the D3, this part. So to be a key point, it must be the highest among the 26 neighbors. So 26 neighbors means 9 layer below, that means below to this one, this 9 and above to this layer, that means into D2 and D2 and D4, right? So in D3, 3 is the greater than all the 8 neighbors,
Ma'am,
right? Yes, yes,
could you repeat the 26 neighbors?
yeah. So neighbors above, here we will take a 3 cross 3 matrices. That means 8 means here, if you take a 3 cross 3 matrix here, so 8 means if you just remove the 3, the maximum, that highest value. So here the 8 values are there. Here 8 into in D3. And if you take the 3 cross 3 matrix, so 9 layer above the to the 3 cross 3, that means we are taking this center matrix, right? So that means layer above and sorry, layer below and layer above in the 3 cross 3. So here the 9 values are there in this 3, 9 values in this 3 and 8 values because we are taking the maximum value out. Okay, so that means the 8 neighbors. So here the total 8 neighbors will be there. So that 9 plus 9 plus 8, it is a 26 neighbors total. Okay,
Yes, ma'am.
so in this below layer, that means D2. So 3 is greater than all the values, right? So if you check here, this center, so 3 is greater, right? In D2 as well. And if you check, this is also a positive number. So if you check the 3 cross 3 center matrix, the 2 is there. In all the D1, D2, D3, D4, only 3 is the highest, maximum highest value, right? In all the highest points, highest value is 2 in D2 and D4. In D2, highest value is 2, D4 is the highest value is 2, and in the D1 as well, highest value is 2. But in D3, the highest value is 3. So 3 is the highest value among all the Gaussian shift detection algorithm that we have calculated, right? So 3 is the absolute maximum compared to all 26 that all the neighbors. So this is our key point because it is a highest or maximum value, or you can just check all the points. You just find out all the values are the -1 or 0, -8, -6. So highest value is 3 only, or that you can say that maximum value is 3 only. So this is our key point, maximum value. So 3 is our key point, right? So now we need to map the 3 into the coordinates because they are asking for the key point location, right? So for the 3, the key point locations are the 3 is provided in the second row and second column, right? In the second row and second column. So what will be the location of this? At x direction, it is at location 1, and at y direction, it is a location 1, right? Like in any matrix, it is a representation of 0, 0, 0, 1, 0, 2, and 0, 3, right? And this one is 1, 0, 1, 1, 1, 2, like that, right? So it is at coordinate location 1, 1, right? Is it fine? So location is x is equal to 1 and y is equal to 1, and scale, that means maximum value is 3, right? So which option can be a correct one? Option B is the correct. So yeah, maximum value is the key point, Anand is. So yeah, so all the maximum value is 3. So this is our key point, and it is at what location this is 3 is located, that maximum value. So it is located at 3311. Shouldn't it be 2 2? So in the matrix representation, if you see that it is a start from the 0 0, not a 1 1. In very rare cases, a typical representation of the matrix is 0 0 0 1 1 0, like that, not a 2 2. Okay. So it will start from the coordinates x is equal to 0 0 2 2. We got twos and threes only. What does it means, Anand? So it 2 2 you can represent also, but it depends on the question as well. So here the at the location 2 2 the scale is 2, but it is not a correct one, right? Because we need to get a maximum value. Okay, in the matrix representation, if any matrix is given, so what is a matrix key point location? Like if a matrix that you can say that zero row, like 0 0 0 1 1 0 1 1, like that only, no? We how we can represent a matrix in a homogeneous form? How in a image processing, how any pixel is represented in a matrix form? So mostly it is in this form. If it is a 2 cross 2 matrix, if it is a 3 cross 3 matrix, so it is a 0 0 0 1 0 2, like that, 1 0 1 1. It is a 1 2, right? Like first row, first column. 0 0 represents the first row, first column, right? The next 0 1 value represent first row, second column, right? So it is representing second row, second column. Is it fine, Anand? It okay. So have you understand it clearly or any doubt, any problem? Okay, so I hope all of you have understand this question. So now can we move to our next question? Okay, so now moving to our next question. So our next question is an image is given below. The image matrix here again it is given. It is a 5 cross 5 matrix. Now they are asking if we apply HOG feature descriptor with 3 cross 3 Sovel kernel in the image, the gradient orientation of the central pixel will be. What will be the gradient orientation of the central pixel? So here the central pixel is also highlighted, that is a 42. What is the gradient of this central pixel? Okay. So here the image matrix is a 5 cross 5 grid matrix that is given, and the central pixel is at third row, and that means third row, and in this third column. So third row is this one and third column, right? And the value it is 42. Now they are asking to apply a 3 cross 3 Sovel kernel, right? So to apply a 3 cross 3 Sovel kernel, now we need to find the 3 cross 3 matrix in the given 5 cross 5 matrix. So what is a neighboring pixel? Because we are just focusing on the central pixel. So what are the neighbor? So this will be the neighbors of this 3 cross 3 pixel, right? To apply a 3 cross 3 Sobel kernel, we need to take the 3 cross 3 in the given image matrix. So what are the given 3 cross 3 image matrix? In here it is. So here is a 187, 92, 125, right? Now next one is a 63, 42, and 71. Now next 254, 80, and 250, right? This is our image matrix, 3 cross 3 image matrix. Now the Sobel operators are in the x and y direction. That means you can say the horizontal and gradient or vertical gradient. The Sobel operator kernels. Can anyone of you tell what are the Sobel operators in the horizontal as well as vertical direction? Anyone would like to tell? Sobel kernels in horizontal as well as vertical direction. Nobody is interested in the answering. Okay, so we'll operate that kernels are, so let's say gx is representation in the horizontal. So minus 1, 0, 1, minus 2, 0, 2, and minus 1, 0, 1 is the horizontal kernel, and the vertical kernel is minus 1, minus 2, minus 1, 0, 0, 0, 1, 2, and 1, right? So first we will calculate the horizontal gradient. So first we need to just multiply the 3 cross 3 given matrix to the horizontal and then vertical. So if you just calculate, just represent it gx, or you can represent some other, let's say vx, we are representing. So w into gx to get the horizontal gradient. It is a, let's say, horizontal gradient vx. Okay. So just multiply this matrix to this matrix. Can you multiply? We simply multiply by row wise, row by row, and So minus 1 into 187, then next plus 0 into 92 plus 1 into 125. It is multiplication of the first row. Now the second row minus 2 into 63 plus 0 into 42 plus 1, sorry, it's 2, 2 into 71, right? Now similarly for the next minus 1 into 254 plus 0 into 80 plus 1 into 250, right? Now just add, subtract all the values. So minus 187 plus 0 plus 127 minus 2 into 63. If you multiply, you will get 1 126, right? Plus 0 plus 142, right? 2 into 71. Now next one is minus 254 plus 0 plus 250. Now if you just add and subtract all the values, you will get here total minus 50. So horizontal gradient you will get minus 50. Is it fine to all of you? Horizontal gradient, how we have calculated? Okay now. So now similarly you have to calculate the vertical gradient as well. Okay. So similarly we need to calculate the vertical gradient. So I'm just removing it from here. So vertical gradient. So W into ZY. So just multiply these two. So minus 1 into 187 minus, so minus 2 into 92. So minus 1 into 125. And the other values, 3 zeros are there. I'm just directly writing because 0 into 63, 0 into 42, 0 into 71. Right? Now next one is plus 1 into 254 plus 2 into 80 plus 250 into 1. So if you just multiply all those values, so you will get minus 187 minus 184, I think, yeah, and minus 125 plus 0 plus 254 plus 160 plus 250. So if you just add and subtract all these values, so you will get the vertical gradient Vy is equal to 168. Okay. Is it fine to all of you? Have you calculated this part? Have you calculated? So I hope all of you have calculated. So Vx we are getting minus 50 and Vy we are getting 168. Okay. So now they are asking the gradient orientation of the central pixel. Okay. So how we can calculate the orientation of the central pixel? Orientation or angle, it is the same. Okay. So the orientation is calculated by, that is theta is equal to arc tan gy by dx, right? You can say that tan inverse, so gy vy, I can write vy divided by dx. So 168 by minus 50 Now, if you just divide it, so you will get minus 3.36, right? Now, if you just calculate it, so you will get minus 73.42599, and that is approximately minus 73.43. So here it is a positive value it is given, right? So we will take it like a positive value. So that is approximately equal to this one. So 73.43. Okay, is the correct answer if you take the positive of this one. So is it fine to all of you? Okay. Okay, so now moving to our next question. So our next question is given a Hessian matrix H, that is the matrix is given 0 0.5, 0 0.07, 0 0.07, 0 0.5. So at an S pixel of the image, compute the ratio of its largest and smallest principal curvature. So how we can calculate this one? Any idea? Okay. So to compute the ratio of the largest and the smallest principal curvature, we first need to find out the eigenvalues of the given Hessian matrix. So how we can calculate the eigenvalues? So the eigenvalues is calculated by determinant of h minus lambda I is equal to must be equal to 0, right? So here H matrix is given 0.5, 0.07, 0.07 and 0.5 minus lambda I is 1001, right? Is equal to 0. It is fine. Now, if you just directly subtract it, so you will get here 0 minus 5 lambda, 0.07, 0.07 and 0.5 minus lambda equal to 0, right? That must be determined must be equal to 0, right? Now, if you just calculate the determinant, so 0.5 minus lambda whole square minus 0.07 square is equal to 0, right? It is. So if you just 0.5 minus lambda whole square, that is equal to 0.07 square, right? So now if you further just calculate the fourth square will be the cancelled out 0 minus 0.5 minus lambda is equal to plus minus 0.07. So now if you just calculate, so lambda 1 or lambda 2, you can say that maximum or minimum you can represent to any value. So I'm just representing lambda max. That means if you just calculate it, lambda is equal to taking the plus value and minus value at a time. So lambda max you will get here 0.57 and lambda minimum value you will get 0.43, right? So have you understand how we are calculating? So just take or lambda 1 lambda 0.5, just take once a positive value. So 0.5 minus lambda is equal to 0.07. That means once take once a positive value. So if we take a positive value, so 0.5 minus 0.07 is equal to lambda. So here you will get lambda mean is equal to 0.43. Similarly, for the next value, take 0.5 minus lambda is equal to minus 0.07. So lambda here you will get 0.5 plus 0.07. So 0.57, right? Is it fine how we are calculating? Here lambda max we will get. So now they are asking to compute the ratio of the largest and smallest principal curvature. So largest means the ratio is equal to lambda max divided by lambda min. So here you will get lambda max is 0.57 and min is 0.43. So if you further divide it, the ratio you will get 1.3256. So that is approximately equal to 1.33. Okay, so correct option is this one. So is it fine to all of you? How we are calculating? Any doubt? Okay, so no doubts are there. So can we move to our next question? Okay, so moving to our next question. I hope all of you have understand. So our next question is here. Consider a 3 cross 3 matrix A. So this matrix A is given. So now compute the gradient of the central pixel along x, that means x direction, and y that is in the y direction using central reference. Okay, x and y axis are represented along horizontal right and vertically downward direction respectively. So they are saying that the x and y axes that are represented by the horizontal right and vertically downwards. Okay, so that means horizontally in this and vertically it is in the downside. Okay, so how we can calculate this one? Already we have calculated previously as well. Any idea, any one of you? So to compute the gradient for the central pixel using the central reference method, so we look at the intensity value of the neighboring pixel along the specified axis. So that means we look at the central pixel to the x and y direction as indicated in the question. Okay, so this matrix A is given. Here our central pixel is no, just here it is defined in the question. Okay, using central reference method. Okay, so already we have just taken one column before and one column above, that one central reference. Option B, Ninadipun. Okay, so here just focus on the question where it is written using the central reference. Yeah, just difference between the one left and one right. Yeah, in x and y direction for both. Yeah. So here our central pixel is this one, right? 30, right? Now in the x-axis, that means in this one, in this direction. So what are the left and right neighbors for the central pixel? In the x direction, neighbors are 40 in the left, right? This one in the left and 80 in right, right? In the right direction. Similarly, in the y direction, what are the neighbors? Y direction neighbors are, so 56 above of the central pixel and 59 the below of the central pixel, right? This one and this one. These are the four neighbors in the left, right, and below our. So gradient along the x direction, along x, it is represented by ix. So that means the difference between the right minus left, or you can say that already we ix plus 1 to ix minus 1, right? If you represent, so 80 minus 40, there will be the 40 only. Similarly, gradient along the y direction, that is iy. So below minus above, so iy will be the 59 minus 56, that is 3, right? So iy will be the 3 and ix is the 40, right? So ix is 40 and iy is 3. So yeah, this option is the correct answer for this question. So they are asking using the central difference. So just take the left, right and left difference and below and above difference. Okay. Yeah, that is correct. Option B is the correct answer for this question. Is it fine to all of you? Any doubt? Okay. So I hope all of you have understand. So now moving to our next question. So our next question is for a binary circle of radius r, the Laplacian response achieves its maximum value at what? So for a binary circle of radius r, the Laplacian response achieves its maximum value at r is by 2 or r by root 2, r square by 2 or r square by root 2. At what Laplacian response achieves the maximum value? Anyone would like to answer for this question? Okay, so nobody is interested. So we will see in the detail here. So a binary circle of a radius r can be represented by a function f of xy, and that is 1 inside and the circle and 0 outside. So when we apply a Laplacian or Gaussian filter, and also referred as a Laplacian response to detect the blob, so we are looking at the scale sigma at which the response is maximum, right? So to normalize the Laplacian of Gaussian response for a circular disk of radius r, that reaches its peak when the scale of the filter matches to the scale of the object. Then it will reach to the maximum of its peak. Okay, so the scale normalized Laplacian response in the 2D Gaussian, that is represented by this one. And for the circular symmetric top hat function, or you can say that for a binary circle of radius r, the maximum response occurs at sigma is equal to r divided by root 2. And here the specific scale sigma is characteristic scale of the circle that is found, and that provide the strongest response from the Laplacian operator. So here circle radius r, and it is a 1 inside of the circle, that is a binary representation, and 0 outside of the circle. So that is represented by r by root 2. Okay, and its peak is maximum at this point r by root 2. So this is the option is the correct answer for this question. So for a binary circle of radius r, the Laplacian achieves its maximum value at r by root 2. Is it fine to all of you? Okay. So I hope all of you understand this question. So now moving to our next question. So yeah, our next question is In the Poisson area calculation, what happens at perfect corner? So option A is Poisson area is equal to the template area, or area is exactly half of the template area, or area is significantly less than half, or area is zero. Which option can be a correct one? Which option can be a correct one? Anyone? Okay, so let's hear in detail. So in the SUSAN, that full form is the smallest uni-value segment assimilating nucleus. Okay, so in the USAN algorithm, so the USAN area that represents the number of pixels within the circular mask that have a similar intensity to the central pixel, or you can say that to the nucleus. So here for the each option we will just go through that. In the USAN, area is equal to the template area. That is incorrect. So this occurs when the mask is placed on in a flat or uniform region. Okay. So since all pixels within the template matches to the central pixel, and the USAN area is at its maximum, that covers the entire template in that case. So that's why this is a incorrect, because for that we need to place the mask into the flat or uniform region. Okay. Now next option is the USAN area is exactly half the template area. So that is also incorrect. So this is the characteristics of the straight edge. So when the central pixel sits exactly on an edge, so roughly half of the pixel in the circular mask belong to the same region as the central pixel, while the other half belongs to a different region, or you can say the different intensity. So that is also incorrect. Now, the next option is USAN area is significantly less than half. So this is defining property for the corner. So at the corner, the nucleus matches only the small wedges of the pixel within the mask. So because of the matching area is smaller, then it would be the straight edge. So the algorithm identifies these local minima to locate corners. So that is the correct. Now our next option, USAN area is zero. So this is a physically impossible, because the USAN area always include at least the central pixel itself. So even at the very sharp point, the central pixel and its immediate identical neighbors will always result in a value greater than zero. So correct option is USAN area is significantly less than half. So option C is the correct answer for this question. Okay. So in the USAN area calculation, so it will be the less than half at for the perfect corner, to create a perfect corner. Okay, yeah, that is a C is the correct answer. It should be significantly less than half. Okay, so is it fine to all of you? Any doubt? Okay, so I hope no doubt. So moving to our next question. So now next question, in SIFT, why are key points with low contrast discarded? Option A, they are too computationally expensive. Option B, they are sensitive to the noise and unstable. Option C, they are always edges. Or option D, they don't have an orientation. Which option can be a correct one? So in SIFT, why are key points with low contrast discarded? Any answers? Okay, now answering for option C. Anyone else? Then we will discuss in detail. Okay, so let's see the detailed solution for this question. So we will go through the options by option. Just, let me- So option A is they are too computationally expensive. So while the shift as a whole computational intensive, not expensive. So the act of keeping low contrast point is not what expensive. So rather filtering them out actually reduces the number of points to be processed in the later step. So it is not a computationally expensive. Removing the low contrast, it is a computationally less expensive. Okay, now next option is they are sensitive to noise and unstable. So in the scale invariant that means shift algorithm, the key point localization involving filtering candidate extrema to ensure the resulting features that are robust and reliable. So they are sensitive to noise. So that candidate that it have key point with low contrast, that means they are having low value in the difference of Gaussian images. And they are highly susceptible to the even a small amount of noise changes. So because their signal to noise ratio is low, so their detected positions and scales can change significantly with the minor variation in the image. And instability, that is a these points are considered to unstable because they are unlikely to be repeatable detected in different views under different lighting conditions in the same scene. So to improve repeatability and reliability of the matching process, Shift applies the threshold, and also called as a contrast threshold to discard them. So yeah, they are sensitive to the noise and unstable. So this is the correct option. And then option C is they are always edges. So low contrast points are not necessarily on the edges. They are simply region or with the low intensity variation. So Shift has a separate dedicated step using the Hessian matrix to specifically filter out these edges responses. But they are also unstable but different geometric regions. And our next option is they don't have an orientation. So every key points that survive eventually filtering is assigned an orientation based on the local gradients. So low contrast points could have an orientation calculator, but it would be unreliable because noise sensitivity as mentioned in the option B. Okay, so the correct answer for this question is option B. They are sensitive to noise and unstable. That's why the low contrast points or pixels are discarded. Okay, is it fine to all of you? Okay, so now moving to our next question. The next question is the term scale space in the shift refers to option A, increasing the image resolution, option B, searching for the features across different levels of the Gaussian blur, option C, measuring the distance between pixel, or option D, converting 2D image to 3D. Now, Ninad is answering for the option B. The term scale space in shift refers to searching for features across different levels of the Gaussian blur. Okay. Okay, so let's see. The explanation is here. So we will go through the options. So increasing the image resolution is our first option. So scale space involves reducing fine details through the blurring and downsampling rather than simply increasing the resolution. Right. So this is a not a increasing the image resolution, not a correct option. Now next one is a searching for features across different levels of the Gaussian blur. In the scale, in the shift algorithm, the term scale space refers to the representation of an image at different scales to ensure that features, that is, a key points, can be detected regardless of their size. So to achieve this, first we need to do Gaussian blurring. that creates a series of images by convolving the original image with the Gaussian filters with varying standard deviation. Okay, and the next one is multi-scale representation. So these blurred images from the scale space where the algorithm search for the local extrema, maximum or minimum to identify potential key points that are invariant to the scale changes. Okay, so that is the correct searching for features across different level of Gaussian blur. Okay, so now our next options are measuring the distance between the pixels. So while this pixel distance are used in the other parts of the algorithm like descriptor matching, so it is an odd definition of for the scale space. And the next one is converting 2D to 3D images. So SIFT is primarily used for 2D feature detection algorithm, and that can be used in the 3D reconstruction. But scale space itself is for the 2D multi-scale representation. Okay, so that is also not a correct option. That can be a part of, but not a scale space. So yeah, correct option is option B. Searching for the features across different levels of the Gaussian blur. Yeah. So is it fine to all of you? Okay. So I hope. Now moving to our next question. So next question is in the Moravec detector, if shift UV results in a very low variance in all direction, the reason is either it is an edge, corner, flat or occluded. In the Moravec detector, if shift UV results in a very low variance in all direction, if there is any shift and that creates a very low variance in all direction, the region is okay. Answer C. That's that is correct. So we will go to the option an edge. So an edge would be show high variance in at least one direction across the edges, not a low variance in all directions. Okay, it will show high variance in only one direction. So that is not a correct. A corner. So a corner is characterized by the significant intensity changes. So that is also related to the high variance in all the directions. Now next one is a flat. So in a Moravec detector, the classification of the region is determined by the evaluating the sum of the square difference. When window is shifting by the various direction, that is typically horizontal, vertical or diagonal. So the flat region, if the shift results is very low variance, so in all directions, the region is considered as a flat. And if the shift results in a low variance in one direction, but high variance in the perpendicular direction, that region is an edge. And if the shift results the high variance in all directions, then the region would be a corner. So correct option is C, that is a flat. Okay, because it is creating a very low variance in all the direction. So occluded is the next option. So occlusion refers to the object being hidden by the other scene or other pixel. So it is not a classification category with the Moravec corner detection algorithm. So yeah, correct option is C, option C, that is flat. Yeah, correct. I hope all of you are getting these questions. So is it fine to all of you? Okay. So now next we move to our next question. Now next question is how many values are in the standard shift descriptor vector is. So any one of you can tell how many values are in the standard shift descriptor vector is. Any idea? Okay. So the shift descriptor is computed by taking a 16 cross 16 pixel neighborhood, right? Around a key point. Okay. So For that, we have to divide it into the 4 cross 4 grid because it is a 16 cross 16 pixel. So for that, we can't calculate directly. So for that, we will divide it into the 4 cross 4 grid, or you can say 4 cross 4 grid of the subblocks. And to creating an 8-win orientation histogram for each subblock. So the script descriptor is computed by taking 16 cross 16 pixel neighborhood around a key point. So that 16 cross 16 point, we will divide it. So dividing it into a 4 cross 4 grid of subblocks. Subblocks okay, and creating an 8-win orientation histogram. Histogram. So one problem we have solved. There is 8-win angles are given, and magnitude and angle matrix is given, right? For that, we have calculated the corresponding gradient magnitude. So, for creating 8-win orientation histogram for each subblock, right? So that this results in the 4 cross 4 grid and into 8 orientation for each subblock, right? So total how many dimensions? So 128 dimensions will be there. So the for the purpose for this one, these 128 not negative values are used to form a feature vector that represents the local appearance of the key point that allow for the robust matching. Okay, the total 128 dimensions for the standard descriptor vector are represented. So yeah, option B is the correct answer for this question. Okay, so is it fine to all of you or any doubt? Okay, so I hope all of you have understand. So now moving to our next question. So now next question is, if the trace of the matrix is 14 and the determinant is 40, what is the Harris response R? So this is a simple practice question for you. So can you calculate and let me know what will be the response R? So here trace of the matrix, let's say Harris matrix represented by M, and how we can calculate the Harris response? So Harris response, yeah, R is calculated by determinant of M minus K trace of M whole square, and where K is the selectivity, right? Response that is vary from 0.04 to 0.06. Already told. So here determinant of Harris matrix that is given as 40 and trace of the Harris matrix that is given by 14. So just put in this equation. So 40 minus K into 14 whole square, right? So here K value is vary from 0.04 to 0.06. So first here K is equal to, we will take 0.04. Okay. So 40 minus 0.04 into 196. So 40 minus 7.86. If we multiply this, so overall you will get 32.16. Okay. So if K value not given, so you need to check for 0.04, 0.05 and 0.06. Whatever option is matching, in the most of the cases it will be the given. The value is given. Okay. So here it is not given. So that just we have taken. Already I have checked for the all these three values. So at 0.04 the option is matching. That's why I have taken directly at 0.04. So yeah, for that
Hello.
option. Yeah,
Yes,
hello.
ma'am.
Yeah.
How can you obtain the value of K?
So already it is specified. It will vary from 0.04 to 0.06. Okay.
It is also
So
defined.
yeah, it is defined. So that
O-
K value will range from 0.04 to 0.06. Okay.
Okay.
So
Okay.
here already I have checked. Actually, I have calculated this
Lowest range is 0.04 and highest range is 0.06 is
06.
defined.
Yeah, it is given.
Okay. Okay.
So I just previously I have checked between for all the three values. So just it is matching with the 0.04. That's why I have taken directly 0.04.
This value of K is defined in all conditions
In all the conditions.
in these questions.
Yeah,
Yeah, all type of questions.
you can just check most of the cases it will be given. The K value will be given to you in
Okay.
the
Okay.
question.
Okay.
Yeah.
Thank you.
So is it fine to all of you? Okay.
I remember, but in these questions,
Yeah.
where the value of K is given,
In this question, it is not given. In this question.
not given.
Yeah. In this question, it is not given.
Acha,
But if question will be asked to you, in that case, it will be the given.
acha. Yes. Okay.
So it is a constant. Already we have defined one more question. It is a K. What K is told to you? It is a selectivity, right? And it will be the vary from 0.0 to 4. Yeah, Ninad Singh, it is given in the slide as well. So, uh, so have you gone to the slides to see? So K is called as a sensitivity constant. So is it fine to all of you? Okay. So now moving to our next question. So our next question is in shift if a key point is detected at a scale of sigma that is 1.6, what is the radius of the region typically used for the descriptor? So here in shift a key point that is detected at this scale, what is the radius of the region typically used for the descriptor? 8 into 1.6, how? 8 direction. No, it is not related to in the 8 directions. So the size of the descriptor region in the canonical shift implementation, that is proportional to the key point scale, that is a sigma. So the radius for that is calculated by is the radius for the shift descriptor for the given scale, the shift descriptor for the given scale is calculated by, that is a scale, that is sigma, into magnification factor and factor. Okay, so shift uses the standard magnification factor, so that is 3. So standard magnification factor of 3 to determine the size of the region. Okay, so radius, that is calculated by scale into magnification factor. So scale, it is here given 1.6 into 3. So if you just calculate, so 4.8. So 4.8 pixels will be there. Okay, yeah, yeah, that is correct. 3 into scale. So option B is the correct answer for this question. So is it fine to all of you? Okay.
Hello, madam.
Yes,
Standard magnification factor is fixed.
is 3. Yeah, it is given.
It is given also.
Yeah, it is a standard magnification factor that is used for the to determine the size of the region.
3.
Yeah.
Okay.
So anything else to see? Okay. So now moving to our next question. So next question is, in shift scale space, if the first octave start with sigma is equal to 1.6 and there are s is equal to 3 intervals, that is scales per octave, what is the exact sigma value of the fifth image in the first octave? So anyone, any idea for this? In the shift algorithm, the scale space is constructed by dividing each octave into the S intervals. Okay, so to achieve this, several Gaussian blur images are produced. Already we have seen for the each octave. So the scale factor between the consecutive image is an octave that is given by, so the scale factor between consecutive images in an octave is given by, that, let's say it is represented by k is equal to 2 by 1 by s. Okay, where s is the intervals. Okay, so now for each image I in the octave, each image I in the octave has a scale value that is a sigma I, and that is calculated by sigma 0 k of I, and just put the value sigma k is equal to 2 1 by s of I, and further you can just write sigma 0 2 to the power I by s. We can write it like this, right? I by s. Now for the each image we have to calculate. So for the first here I is the image. So for I is equal to 0, let's say it's image 1. So sigma 1, you can say that 1.6 into 2 to the power 0, right? 0 by s, or s is given as 3. So sigma 0. So directly 1.6 we will get. For I is equal to 1, you can calculate the for the next sigma is equal to 1.6 into 2 to the power 1 is so 1 by 3, right? So 1 by 3. So further you can calculate it, otherwise you can leave it because it is given in this form also. So now for the next I is equal to, because they are asking for the fifth image in the first octave. Okay. So this is our first octave. So for the I is equal to 5, we need to calculate. So sigma is equal to 1.6 into 2 to the power 2 by 3, right? Now for the next image I is equal to 3, sigma you will get is equal to 1.6 to 3 by 3. So 1.6 into 2, so 3 by 0.2. You can directly calculate it. For the I is equal to 4, that means which image? Fifth image. That this is our fifth image. So image fifth will be the sigma is equal to 1.6 into 2 power 4 by 3. So for the fifth image, this is our answer. For the fifth image, 1.6 into 2 to the power 4 by 3. So it is directly given. So don't need to calculate. For the fifth image, we need to check. So if you check that, this is our correct option for this one. So is it fine or any doubt? Okay. So can we move to our next question? Okay. So moving to our next question now. So our next question is, given a Hessian matrix H that is given, calculate the ratio of the principal curvature, that is R is equal to alpha by beta, and determine if this point would be discarded by 6 if the threshold is R maximum, that is given then. We need to determine the principal curvatures and then check whether this point will be discarded by 6 or not. The threshold value or maximum, that is given 10. So how we can calculate this question, or how we can solve this question? So how we can calculate first the principal curvature? So principal curvature, as we know, that is calculated by using the characteristic equation, right? So characteristic equation, that is h minus lambda I is equal to 0. The determinant of h minus lambda I is equal to 0, right? So here h is given with 10, 4, 4, 2 minus lambda 0, 0, lambda is equal to 0. So 10 minus lambda 4, 4, 2 minus lambda is equal to 0. So 10 minus lambda and 2 minus lambda minus 16 is equal to 0, right? So now just make a equation. So lambda square minus 12 lambda plus 4. Overall, if you just calculate it, so you will get this equation. Now for that, we calculate the eigenvalues and then find out the maximum and minimum values, right? So that are the principal curvature. So how we can find out the lambda values? Anyone? So can you calculate and let me know what will be the values for the alpha and beta? Or you can say maximum or minimum value, or you can say the eigenvalues. So just calculate this using the lambda is equal to minus b plus minus b square minus 4ac, right? Divided by 2a. We have to calculate using this one. So here b value is minus 12. So 12 plus minus 12 square minus 4 into 4 divided by 2. Now just further you solve all these values. So you will get lambda values, that is 6 plus minus 4 root 2. Okay, if you calculate. So here the maximum value, that is 6 plus 4 root 2. If you just solve it, so you will get approximately 11.66. Just calculate the root 2 value, multiply it and add it. Now next one is a beta. So 6 minus 4 root 2. So if you just further calculate, so you will get 0.34 value. Now in the question they have asked calculate the ratio of the principal curvature. So we have got the principal curvature alpha and beta values. Now calculate the ratio. So just removing it from here. Okay, so R is equal to alpha divided by beta, that is also given. So alpha is 11.66 and beta is 0.34. If you further divide it, you will get 33.97. Okay. So now next they have asked determine if the point would be discarded by shift if the threshold is our maximum, that is given is equal to 10. So in the shift key point, that is discarded if they are located on the edges, right? They will be discarded if they are located on the edges. So the condition to keeping the point is, that is calculated by threshold of, trace of h square divided by determinant of the Hessian matrix, that must be less than equal to R max plus 1 whole square divided by R max. Okay, so the condition to keeping that S point is, this is a condition for that. Now, can you calculate the trace and determinant of the Hessian matrix? Can you let me know what will be the trace of the Hessian matrix? Trace of this one. So, what is the trace? Can you let me know? Trace is the diagonal values of the matrix, right? So these are the diagonal values. So 10 plus 2, 12 is the trace and determinant is 10 into 2 minus 4 into 4. So 20 minus 16, that is a 4, right? So we have calculated. So now for that, so trace square divided by determinant, that is first we will calculate it. So 144 divided by 4 here, this side, and this is equal to 36. Now similarly we have to calculate this side also. R max is given 10, so 10 plus 1 11 square divided by 10, so 121, right, divided by 10, so 12.1, right. So here it is given that if the threshold is, so that point would be discarded if the threshold is R max is equal to 10, right. So here R max, so here, yeah, 36 is greater than this threshold 12.1. So that means that will be the discarded because it is a greater than, right. So in the option it is just a misplace or mismatch, right. So otherwise it will be the option 1. So here no options are the correct because the exact value it is not given. It should be 12.1, right. So it should be if the here the if this side 36 is greater than to 12.1, it should be discarded, but exact value is not same. So that's why no option is correct here. Yeah. No. So is it fine to all of you? Any doubt? Okay. So now moving to next two more questions are there. So now next question is, which of the following best describes orientation assignment in SIFT? Option A, it rotates the entire image to a standard 0 degree view. Option B, to ensure the descriptors is invariant to affine transformation. Option C, it makes a descriptor invariant to rotation by describing gradient relative to the dominant local orientation, or it aligns the key point to its closest image edge. Anyone like to answer for this question? Okay, so we will go through the explanation. The orientation assignment is the third major stage of the SIFT algorithm. So it primarily pur- uh, purpose is to ensure that resulting feature descriptors are invariant to image rotation. So that meaning the same object can be recognized if the camera is tilted or object is turned. Okay, so for that, for what we need to do, is calculate the local gradients for each identified key point. So the algorithm examine the neighborhoods of the pixel at the key points of specific scale, and that calculates the gradient magnitude and direction for the every pixel in that region. Now next process is building an orientation histogram. So an orientation histogram is created with 36 wings, each covering 10 degrees. Total 360 degrees. So for each pixel gradient orientation, that is added to the corresponding wing by weighted by its magnitude and Gaussian window. Now next in determining the dominant orientation. So the highest peak in the histogram represents the dominant orientation of the local patch. And if other peaks are within 80% of the highest peak, then additional key points are created for those orientation to improve stability. Now next is achieving the rotation invariance. So to achieve the rotation invariance, the subsequent descriptors computed and all local gradients orientated are rotated related to the dominant orientation. Okay, so now next option is if does not rotate by the entire image, it only rotates the local coordinate system individual key points. Okay, so it will not rotate the entire image. It rotates only local coordinates. And option B that is given, while shift descriptors are robust to a small affine changes, so the orientation assignment steps specifically target rotation invariance. Okay, so now next option that is C is given, orientation is based on the distributed of the gradient in the neighborhood, so not just the closest edges. Okay, so correct is the option C, that is orientation assignment achieves the rotation invariance by representing local gradients that related to the domain orientation found at key point neighborhood. So option C is the correct answer for this question. So actually this one is a D for the option D. Okay. So is it fine to all of you? Okay. So now next and last question. So in the Harris corner detector, if we increase the value of sensitivity parameter K, for example 0.04 to 0.06, what is the expected result? Option A, detector becomes more sensitive to edge. Option B, the detector becomes more selective, identifying only the sharpest corner. Option C, the detector identifies flat regions or corner as a corners. Or option D, the response are increased for all points. So can you answer for this question? So this one is I think easy one. In the Harris corner detector, if we increase the value of sensitivity parameter K from 0.04 to 0.06, what is the expected result? Okay, someone is asking for option B. Okay, we will see. So here the explanation is given. So option that is given, the detector becomes more sensitive to edges. So increasing the K value actually does the opposite. So edges are characterized by the one large and one small eigenvalues. Right? So increasing K that makes K trace term larger and which pushes the response R further into the negative region for the edges and that making them easier to filter out. Okay. So and option B is the detector becomes more selective and identifying only the sharpest corner. In the Harris corner detector, the corner response R that is defined by this formula already we have seen. So where M that is a second moment matrix and lambda 1, lambda 2 are the product of the eigenvalues. That is a determinant and trace is the sum of the eigenvalues. Okay, so the impact for the increasing K, so the parameter K that is typically ranges 0.024 to 0.06 is the sensitivity factor already we know that. So because K is used to subtraction term, so increasing the value decreases the overall response R for any given point. And the selectivity for the point to be considered as a corner, its response R must be exceeds to a certain threshold. So by increasing K, the value R drops and that means that only those points with very large lambda 1, lambda 2 will remain above the threshold. So that makes the detector more selective and less likely to misidentify edges or noises as a corner. Okay. So yeah, option B is the correct answer. So the detector becomes more selective and identifying only the sharpest corner. And the other options that are given, the detector identify flat regions or corner. So in the flat regions, both lambda 1 and lambda 2 are the near zero and that results in a very small r regardless of the case. So increasing k does not change the fundamental classification for that. So the response R increases for all the points. So as shown in the formula, already we have seen that for the response, since k is the part of the subtractive term, so increasing k response decreases the value of R and the all points where the trace of the matrix must be greater than 0. So option B is the correct answer. The detector becomes more selective, identifying only the sharpest corner if we increase the sensitivity parameter K. Okay. So now questions have been completed. So if you have any doubt, you can ask. Otherwise, we can close the session. So thank you everyone. Thank you for joining the session. So if you have any doubt, you can ask. Otherwise, we can close the session. And now you can give the feedback as well for the if questions are okay or I know it is a little bit out of question, out of course, or it is related to you, but it's not exactly what they have asked. So first, I am trying to do the previous year question paper, previous year question, what we have got from the NPTEL. First, we will solve that question. Then we will move to the next more 10 more questions related to basic theoretical and conceptual some numerical problems as well. So is it fine to all of you? Or any doubt or any suggestion you can give here? Very well. Okay. So can we close the session now? If you don't have any doubt, so we can close the session. Okay. So thank you everyone. Thank you for joining the session. Now you can leave the session. Okay. If you don't have any doubt. What I have said, okay, about the question. So I'm just asking for your feedback whether the questions are fine with you. I mean, is it okay? So first, what we are first solving, we are previous year. First 10 questions are related to previous year assignment problems, what previous year they have given. Then we will solve some 10 more questions with theoretical or conceptual and some numerical problems as well. So is it fine, or if you want some more questions? Okay, okay. So if you have any doubt, you can ask, otherwise we can close the session. Okay, so you can leave the session if you don't have any doubt. Okay, so thank you everyone. Thank you for joining the session. I'm just closing the session. Okay.